Hello everyone, welcome again to tutorial number 8 on static equilibrium. So we're going to solve this tutorial sheet using the two conditions for equilibrium. So the first condition requires that the vector sum of all the forces acting on a system are equal to 0. That means if you have forces in the x, forces in the y, or even the z, if it's a three-dimensional system, the sum of those forces must equal 0. Okay, so in our language we usually say they must cancel out. If you have a force on the left, it must be cancelled with a force on the right. If you have a force acting upwards, it must be cancelled by a force acting downwards. Okay, so that is the first condition of equilibrium. Then the second condition requires that the vector sum of the torque acting on a system must also equal 0. Okay, so we're going to use these two conditions to solve some of the problems in this tutorial sheet. So we begin with question 1. We have this system. Okay, we have a system and we are required to find the value of T1, T2 as well as M2. Okay, so the system is in equilibrium here, and when we look at the tensions, they are making an angle with the x axis. Okay, so then we are going to consider the forces. Okay, the forces in the x as well as the forces in the y. All right, so the first thing that we need to take note of is that the tension T1, okay, T1 is equal to M1 times G, or rather T1 is equal to the weight of M1, okay, that we know, and we are given the value of M1 and we also know the value of G, so already we can find the value of T1 from T1 equals M1G, which is going to give us 10 kilograms times 9.8, and we're getting 98 newtons. Okay, so the mass for M1 is 10 kilograms, so the weight of this mass is simply equal to T1. Okay, so knowing that, we move further. The sum of the forces in the x, we consider the x forces. We have the sum of the forces in the x are equal to T1 cos 45, because it's making an angle of 45 with the x, minus T2 cos 53 must equal 0. So the sum of the forces in the x must equal 0 for this system. Okay, so this further gives us T1 cos 45 being equal to T2 cos 53, all right, from which we can find an expression for T2. Since we already found T1 as 98 newtons, we can also solve for T2. Okay, so we can make T2 the subject here. We can have T2 equals T1 cos 45 divided by cos 53. Okay, substituting the value of T1, we'll have 98 times cos 45, giving us 69.3, divided by cos 53, which is 0.6. If we divide that, we're going to find T2 as 115.5 newtons. Okay, so we have found T1 as well as T2 from this question. So now we have to find the mass M2. Okay, the diagram here, we find the mass of this M2 here. Okay, So to find the mass of M2, we are going to have to consider the forces in the Y, okay, from which we can find an expression for the weight of M2, right? So also the sum of the forces in the Y must equal 0. That is a condition for equilibrium. Therefore, we have that in the Y, we are finding T2 sine 53 plus T1 sine 45 minus the weight of M2. We're supposed to get a 0. Okay? Therefore, we can have that T2 sine 53 plus T1 sine 45 is equal to M2 times G, which is the weight of M2. Okay, therefore we can make M2 the subject of this formula. So we find an expression for M2 from this. We will have M2 equals T2 sine 53 plus T1 sine 45 over G. If we work this out, we are going to find our M2 being equal to 16.5 kilograms. All right? So for this system, notice that we've only used the first condition of equilibrium that deals with the sum, or rather the vector sum of the forces. So we've had our x forces, the net x force being equal to 0, as well as the net y force being equal to 0, and we're able to obtain all the values for T1, for T2, as well as for M2. Okay, so we move on to question 2. There we go, question 2. Okay, so here consider this system. All right, we are required to find the weight W2, okay, also W3, okay. So as the question is saying, find W3 and W2. Okay, so first off, take note that T2 here is going to be equal to W3. Also T1 is going to be equal to 800 newtons there. Also notice that the tensions are making an angle, this time with respect to the y-axis and not the x-axis. Okay, so therefore we are going to say that T1 is equal to W1, which is 800 newtons. Okay, then the sum of the forces in the y, because the tensions are making an angle with respect to the y, is going to be the sum of forces in the y equals T1 cos 40 plus T2 cos 50 minus, okay, minus W2 is equal to 0. Okay, so this is the sum of the forces in the y, and we can find an expression for W2 by taking W2 to the other side. We have W2 equals T1 cos 40 plus T2 cos 50. Okay, so let this be our equation 1. So we move further. Let's consider the forces in the x. The forces in the x, because the tensions are making an angle with the y, we're going to have the sum of the forces in the x equal to T1 sine 40 minus T2 sine 50 equals 0, implying that T1 sine 40 is equal to T2 sine 50. Okay, so there's a mistake here. It's supposed to be sine 50. Okay, so T2 sine 50, like that. All right, therefore we can make an expression for T2 from this. We'll have that T2 equals T1 sine 40 over sine 50, giving us 800 sine 40 over sine 50. Therefore, our T2, which is equal to W3, is going to be 665 newtons. So from this, we are able to find, we have found a W3 already. Therefore, using equation 1, okay, equation 1 right there, we can now solve also for W2. So using 1, we can find W2, okay? So equation 1 says T1 cos 40 plus T2 cos 50 equals W2. Therefore, W2 equals 800 cos 40 plus 665 cos 50, giving us W2 as 1044 newtons. Okay? So 1044 newtons, that is W2. It's very simple. Okay? So notice all the steps that we have considered here, and also the orientation of the system, making an angle with the y, okay, slightly different from the first case where the angle was with respect to the x. All right, so we move on. Question 3. So question 3 here, we have a board which is suspended by 2 ropes as shown in the figure. Okay, so we want to find the angle theta, this angle here, this one. We want to find the angle theta, which is made by the left rope. Okay, we also have to find T1, T2, all right, the tension T1 on the right as well as the tension T2 on the left. Okay, so this system, when we look at it, this is a board, all right, so we're going to have to consider all the conditions of equilibrium where they're applicable. Okay, so let's try to consider the first one. First off, we know that these tensions are also making angle theta, the other one an angle of 30 with respect to the y, right? Therefore, we are going to have that in the x, we are getting T2 sine theta minus T1 sine 30 equals 0, giving us T2 sine theta equals, we know that sine 30 is 0.5, therefore we're getting T2 sine theta equals 0.5 times T1, giving us T1 equals 2T2 sine theta. Okay, hope you're following that. So let this be our equation 1 for now. So now we move on to the y. We're getting T2 cos theta plus T1 sine 30 minus the weight of the bar, which is 120, minus the weight of the block, which is 400, must equal to 0. Okay, so this is the sum of the forces in the y. Therefore, from this we can take, or rather subtract, the 120 and the 400, giving us a minus 520, which we can take to the other side and remain with T2 cos theta plus T1 cos 30 equal to 520. Okay, so from here we can find an expression for T2. We'll have T2 equals 520 minus T1 cos 30. Therefore, we can further express cos 30 and get T2 equals 520 minus 0.866 times T1. Okay, so this is our expression for T2. Now, we know what T1 is from equation 1. We can substitute this expression for T1, okay, this equation here, we can substitute it into here. Okay, so if we do that, then we are going to have that T2 cos theta, okay, minus, rather equals 520 minus 0.866 times T1, where T1 is 2T2 sine theta. Okay, therefore we are going to have that T2 cos theta equals 520 minus, if we express this, we are going to get 1.732 T2 sine theta. So this can be our equation 1. Okay, so I think I've noticed a slight mistake somewhere here on this part. Okay, so here is not supposed to be T2 only. Okay, it is T2 cos 30. It is T2 cos 30. Can make that correction. All right, same happens here, T2 cos 30, like that. Okay, so we proceed. Therefore we have equation 1 and we have come up with equation 2 from those. So now we consider the second condition for equilibrium. Okay, so for this system both conditions apply. So the second condition requires that the vector sum of the torque, or rather the torques, must equal 0. Okay, and we have our system. According to this system, our 400, or let me start with the 120 mass, or rather the weight of this board, is located at the center. Okay, so if this board has a length of L, then we are saying that its mass, or the center of mass, is at L over 2. Okay, and now we are saying that the 400 newtons weight is also located at L over 4. All right, so therefore if we are considering the torques, we are going to say the 400 newtons is at a length of L over 4, which is the same as 0.25 L, and the 120 newtons, which is the weight of the board, is at L over 2, which is the same as 0.5 L. Okay, and also we have another force, okay, the T1 cos 30, which is applied at a length of L. Okay, the T1 cos 30 being applied at that point. Okay, so I'm unable to mark the T1. Okay, so the T1 cos 30 is also applied at the distance of, or rather a length of L, in the negative direction. Okay, so if we sum up the torques for this system, we're going to have the sum of the torques is going to be 400 times 0.25 L plus 120 times 0.5 L minus T1 cos 30 times L, which must equal to 0. Okay, which must equal to 0. Right, so then we can say 100 L plus 60 L minus 0.866 T1 L equals 0, from which we are getting 160 L equals 0.86 T1 L. Okay, and from this we are able to find the value of T1 by dividing 160 over 0.866, and we're getting T1 as 184.8 newtons. So we have found T1. Okay, so if we go back to equation 1, equation 1 tells us that T1 is equal to 2 times T2 sine theta. Okay, so from which we can obtain an expression of T2 sine theta equals 0.5. Okay, when this 2 goes is the 2 here, this one, okay, it's going to divide with the T1, therefore we remain with T2 sine theta equals 0.5 times 184.8, and we are obtaining T2 sine theta as 92.4. okay, so let's call this one 3 for now because it has got two unknowns, which is T2 as well as theta. Okay, so at this stage we can now try to find the value of T2 by considering equation 2, which gives us T2 cos theta equals 520 minus 1.732 times T2 sine theta. Okay, but we know that T2 sine theta is this guy, which is equal to 92. So where there's T2 sine theta here, we replace or substitute with 92.4. Therefore, we are going to have that T2 cos theta equals 520 minus 1.732 times 92.4. okay, from which T2 cos theta equals 360. Alright, so this could be our equation 4. So if we divide equation 3 by 4, we can get tan theta. Okay, we can do that. We are saying tan theta equals equation 1, and we are going to have 92.4 over 360, giving us tan theta equals 0.257, from which we are able to obtain the value of theta. Okay, and we are finding theta to be 14.4 degrees. So after having found theta, now we can easily find the value of T2 by substituting the value of theta into T2 sine 14.4 equals 92.4. okay, from which T2 is going to be 370 newtons. Okay, so I hope I'm not too fast for this, but yes, I'm trying to be a bit fast. Okay, so yeah, don't worry if it's not clear, you're always free to ask. Okay, so that is how we go about this system. So we have found the value of T2, T1. Okay, so notice that for this question we have actually used both conditions for equilibrium. Okay, they have been applied for this particular system. All right, so let's move on to the next question. We have question 4.